Olin, why is this thing called a scan converter necessary in changing the pictures that we see from the television cameras on Apollo spacecraft into those that we can see here on Earth, both here in the United States and in other nations?
Well, first of all, we're bandwidth limited. We only have a 500 kilohertz bandwidth to transmit the picture down. This necessitates a slow scan type of television to be utilized on board. We have to convert this slow scan television system into a picture that's compatible with the home television receivers here in the States. And our onboard system is operating at 10 frames per second. The commercial standard in the States is 30 frames per second.
That means 30 individual pictures flash toward the eye per second, right?
That's right. We have a 2-to-1 interlace, and so there are actually 60 in the home commercial receiver. But if we consider just 30 for a moment, we have to upscan the 10-frame data into a format compatible with the home set, which necessitates a scan converter.
And that's why the scan converter. And how does it work?
We look at the slow scan monitor with a commercial camera that's operating at 30 frames per second, and this rephotographs the slow scan monitor into the commercial standard used here in the States.
Well, now, scan converters are also used in commercial television around the world in converting the American system to the English system to the French system and so on. Is that not right?
Yes, that's correct.
Is the basic method the same?
It's somewhat similar. Many of these scan converters are optical scan converters like we're using.
Is there an all-electronic system which can take all of the electronic bits and store them up and then redistribute them into different types of television transmission systems?
Yes, these are available. However, they're quite costly because of the memory that's required. We're storing like 1 million data bits when we start talking about television, and this necessitates a rather large storage device.
Meaning a built-in computer?
That's right.
Paul, how does the television camera and transmission system, which we will see on the lunar module, compare and or differ with that on the Apollo craft? We've already seen 2 nice missions with that camera on Apollo. How about on the LEM?
The television camera that's used on the LEM is quite similar to the one that was used in the command module. It does have 1 or 2 additional features. One of them is a feature to scan a picture in a slower mode and therefore give us greater resolution. This, however, limits us to a rather still picture rather than a moving picture as we had in the 10-frame mode. The other feature that this camera has is an extremely low light level sensitivity. We can actually telecast scenes that are very low lit, that don't have much light in them.
Mm-hmm. Does that mean that we might expect to see more contrast, more elements of the grayscale on pictures that come back from the moon in the future?
Well, it so happens that this camera probably does have a slightly better grayscale rendition than the command module camera. However, it doesn't really mean, this low light level sensitivity doesn't mean that this causes this. What the low light level capability does give us is simply the ability to look at a scene which is not as brightly lit as what you would normally expect.
On the Apollo camera, there was an electronic mechanism for controlling the amount of light transmitted. In other words, sort of an electronic aperture. Is this feature also on the lunar module TV?
Yes, the command module television camera did have an automatic light control, which was actually manually controlled in a sense, because you could switch it in or out of the circuit. The LEM television camera is completely automatic. So the light control, in other words, is completely automatic. It does have that feature.
That means that no matter what you point the camera at, whether it's light or dark, whether you're photographing a very bright picture or something that's dimly lit, this electronic circuitry will automatically take care of it for us. Is that correct?
Well, that's correct, within a certain dynamic range. Of course, we can go beyond the excuse me, beyond the extremes of the camera dynamic range. We do vary it by changing the lenses. The lenses itself give you some attenuation of the light, so that if we wanted to look at a very dark scene, we would use one lens. If we wanted to look at a very bright scene, then we use a different lens.
For the camera experts who may be listening, what sort of lenses will be used on the lunar module camera, television camera?
Well, we have 4 lenses that could be used. One of them is called simply a wide-angle lens. It's got an 80-degree field of view. It's good for scene illumination up to approximately 100 foot candles and down to approximately, maybe a tenth of a foot candle. Second lens we have is a lunar night lens. Now this is a very unique lens. It's a very large aperture type lens, so that we can look at scenes that are in as low as let's say 0.01 foot candles in illumination. Then we have a lunar day lens, which allows us to look at scenes as bright as 10,000 foot candles. We also have a telephoto lens, 100 millimeters, that allows us to look at a 10,000 foot candle scene.
Now, how about focal lengths of these various lenses?
Well, we specify the telephoto lens by its focal length, which is 100 millimeters. The wide-angle lens, we don't really think about it in terms of focal length because it doesn't have too much meaning for us. We'd rather talk about it in terms of its field of view. It turns out to be 80 degrees. The lunar night lens and the lunar day lens have 35-degree field of views, and we also specify these by the field of view rather than the focal length.
Paul, what about the temperature ranges that this camera will have to tolerate in space, particularly when you get onto the lunar surface with it?
Well, the camera has a very unique physical design. It's actually physically configured to reflect much of the heat radiation that comes off of the lunar surface. It also has a heat radiating surface on top of the camera that allows heat to radiate out to deep space. So we can use this camera in extreme temperature ranges.
Who designed the camera and who built it, and how will the signal be transmitted back to Earth?
Well, the camera was designed by a combination of NASA engineers and Westinghouse engineers. It is built by the Westinghouse Electric Corporation. The signal itself is transmitted back to Earth by feeding the television signal into the spacecraft transmitter. The transmitter then beams the signal back to Earth just as it does the conventional communication signals.
This will just be part of that unified S-band transmission?
That's correct.
The TV is on our flight. It's a different kind of TV system than we've had before, and the primary reason that it's there is to evaluate the lunar surface TV camera and the transmission system, which in this case is the LEM S-band. And because of the crowded timeline, we are not going to have time to optimize the beauty of the picture. It's going to be really, we're going to have to turn the TV camera on and place it someplace. Most of the time, we only have 2 TV passes. The TV camera only works in the LEM. It doesn't work in the command module, the way it's wired up right now. So we're going to put the TV camera in the LEM, and the busiest days that we have are the LEM days. So it's going to be a matter of taking the TV camera and placing it someplace where it can take care of itself, so to speak, and turning it on. And the idea is not to produce an interesting, unfortunately, it's not to produce an interesting picture for the ground. It's to be turned on, and whatever comes down via the S-band TV link is what we're going to see, what you're all going to see on the ground.
Al? Are there any significant open items now that could affect the February 28th launch date?
I don't think there are any significant items.
Spacecraft or launch vehicle?
No, the closer you get to launch, the more significant the little things become. No, I don't think so.
Passage of about 30 days, I guess.
Yeah, that's pretty significant.
Art Snyder?
Referred to as pimp house, and the LM has been referred to as flimsy. What kind of a house would you call it? How would it compare, say, with the Gemini for comfort and for complexity?
The lunar module? Well, first let me put the comments that I've made in the right perspective. I tried to show that the two spacecraft are different. You look at that thing and it's got things sticking out all over. If you look at the F-14, it doesn't look like that. That has to fly through the air. This doesn't. It's made like that on purpose. It's not an accident that we've got all these protrusions all over. If we made it like this, there's not a chance in the world we'd ever get to the moon. There's not a chance. It has to look like that or we're not going to get there. Matter of fact, if we tried to land that, it doesn't have any landing gear and it would be a pretty hard landing. This spacecraft is designed to handle the people living in it as you go to the moon. This spacecraft is not, and it's very crude from the standpoint of living conditions. I wouldn't give you $2 a day for a room in it, but it's designed to get us to land us on the moon. I think the comfort between there and there is much different, but it's not designed for comfort or anything else like that. If we designed a command module like the LEM, we probably would have a very difficult time getting to the moon. You just can't stay awake forever, and it's very difficult to sleep in the LEM, I think.
In the past couple of flights, the mouth of the slaw has been filled with chaff and other ersatz material. What are your constraints as to going in and getting the LEM? And in past flights also, they seem to have developed into the last hurrah for the spacecraft commander. What's your outlook for future flights, Colonel?
David, answer that one.
Now's our chance, Dave.
Well, to answer your first question, I guess, as Jim has described, the sequence of events within the mission dictate that there are probably very few constraints relative to going in and getting the LEM, because if we don't get the LEM, we don't have a mission. So I think we will, under almost any circumstance, attempt to dock and extract the LEM.
You mean you barrel through chaff or...
No, I don't mean we'll barrel through chaff. Well, I don't, from what I've heard from Apollo 7 and 8, there isn't anything there significant which will get in our way or harm the spacecraft. As a matter of fact, Frank Borman pointed out specifically that the slot panels went aft away from the S4B, which is what they're supposed to do. And I think the whole system was designed to give us the capability to get in there and dock. And I don't anticipate any problem with that, with the chaff and the extra pieces whatsoever. As far as my commander's future, I hope he hangs around, but he can answer that.
Well, I think after the flight I'll probably just keep cutting my hair shorter and shorter so the gray doesn't show, and maybe use a little dye so I look like you and nice dark hair. See, I'm not making any retirement announcements, I'll tell you that.
Gentlemen, since the docking with the LEM is so crucial for this mission, should there develop any problem with extracting the LEM from the S4B, is there any possibility of somebody going EVA to correct the situation?
No, there really isn't. Unfortunately, the EVA equipment is in the LEM.
Jules?
And that's by design also.
Jim, since the LEM is so uncomfortable to sleep in, by your own account, but since the first, second, etc. lunar landing crews do have to sleep in the LEM, why haven't you and Rusty scheduled a trial sleep period in the LEM on this flight?
Well,
In the altitude chamber, I saw him asleep many times. I don't care what he says about not sleeping in it.
As a matter of fact, when I call them on the systems day, very seldom do I get a good, quick answer. I got the feeling that they're not doing anything. They're sleeping over there.
There's a big difference between 0G, because all you've got to do is let go and float in your sleep. 1.6G, you're either sitting on the floor or the ascent engine cover. There are very few horizontal flat surfaces. The ascent engine cover and the floor, and I guess that's where they're going to have to sleep.
How practical an arrangement is that, by the way?
I've never done it in 1.6G. I've never even done it in 1G. You can scrunch down in different positions and fall asleep for a while. I would think that it would be better in 1.6G. How much better, I don't know. It certainly won't be like 0G.
Even we have a hard time falling asleep in a 30-second parabola.
Ed, go ahead, Joe.
I'm not clear on the EVA. You say you had 2 daytime passes. Does that mean you would be outside during the one nighttime pass between?
That's correct.
And will you be out on the porch, as you put it, or in half out of the command module?
No, it'll be on the porch.
On the porch.
It's about a 2-hour period.
For the whole 2 hours. And how long will the command module be depressurized during the EVA?
The same 2 hours.
Ed?
During the EVA, will you have voice communications with both the command module, the LEM, and the ground with resulting inputs from all three?
Yes, the way that works, very briefly, that can get extremely complex.
Why don't we just say yes?
Yes.
I don't understand the communication system, and I've been studying for 10 years, and I don't think...
You can talk silently. When he speaks, all three will hear, assuming you're in ground.
What happens to the lab after the mission? Is it going to stay in orbit?
You want to take the mic there?
How long?
It's going to go into an orbit, I think that's about a couple 100,000 miles by something or other.
How long after the mission?
Forever, probably.
Are you going to use it again?
No. Maybe you missed something. When we go from the LEM back to the command module, then we'll separate the lunar module. It'll be out all by itself. And then under ground control, in an unmanned configuration, under ground control, we'll fire the ascent engine to fuel depletion, which will put it in a very, very high orbit, a couple of 100,000 miles. What is it? No, shoot, I'm sorry. It's only 4,613 by 127. But it'll be up there almost forever. No. The LEM doesn't have much of a protection against radiation, so we wouldn't want to man it in that configuration. It's going through the radiation belts.
Mr. Fenner, how did you design and perfect the rendezvous radar so that you know that it will work on the first manned lunar flight?
Well, the first problem of trying to conceive and develop a radar system is achieving the functions, or getting down in paper what the things are the radar has to do. Now, this involves the variation or the range of ranges, so to speak, that the radar has to measure, the closing velocities between the vehicles, range rate that it has to measure, and the angles over which it has to measure, and the angular accuracy. Now, well, these things can be defined in terms of orbital mechanics, and you come up with a set of parameters on paper that the radar must measure and measure. The next problem then is coming up with a radar system on how to do this. This involves the development of the black box hardware, so to speak. What type of antenna you'd use, what type of radar system, and there are various types of radar systems that work different ways. In this case, we have a parabolic or dish antenna, which is mounted, the dish that's mounted in the front of the LEM, right above the windows. It's about 2 feet in diameter. Once you've converted your radar requirements into a set of hardware, you have a black box, so to speak, that is capable of performing these things by design. You next set about proving that it's capable of doing this. Now, obviously, we can't practice a rendezvous with spacecrafts to verify our radar system, because that's what we're building it for to begin with. So we have to, and in addition, the cost of verifying a radar system on spacecraft, you are using actual spacecraft, is very expensive. So we took the next best step in both the Apollo and the Gemini program. We used aircraft. Now, aircraft cannot fly as high nor as fast as spacecraft, but certainly we can fly certain portions of any rendezvous radar mission, which we did in the Apollo. We did this out at the White Sands Missile Range, where we have extremely accurate tracking equipment, and we flew little bits and pieces of the rendezvous mission as best we could. We started out flying very close, within a few miles. We opened our range up, tracking the aircraft carrying the transponder to about 200 nautical miles, which was the limit of what we could do with aircraft. As a final proof of how well we could track and how far we could track, we managed to put a transponder in Apollo 7, and we were able to track this from the ground at White Sands with a rendezvous radar during the Apollo 7 mission. At this point, we felt that we had done all of the testing we could possibly do from a systems standpoint, so to speak, to prove that we had a rendezvous radar capable of being used on a rendezvous.
How far did you track Apollo 7? Do you remember?
Well, we were able to track reliably to 400 nautical miles on Apollo 7. This is 400 nautical miles slant range.
That would be well over 500 kilometers away for those who deal in kilometers overseas.
Kilometers, it certainly would be, yes.
Then you feel quite confident about the reliability of the rendezvous radar system then when it goes into manned flight on the lunar module?
Oh, very highly, very much. I feel it's a highly reliable radar system. It's been proven over and over again. I feel that certainly we won't have rendezvous radar troubles on any of the rendezvous anyhow.
Okay, thank you very much, Dick Fenner, the Radar Subsystems Manager for Project Apollo. Mr. Stonecipher, the Mobile Quarantine Facility, or MQF as it's coming to be called, will be tested on Apollo 9. First of all, tell us what the MQF is and then how the test will be run.
The Mobile Quarantine Facility is a sophisticated house trailer, if you might like to refer to it as that, and we'll use this facility to house the astronauts from the recovery area to their return to the Lunar Receiving Lab here in Houston.
This is the quarantine facility that's to be used with astronauts who land on the moon, but not in the 9 flights, is that right?
That's correct. We'll use this facility after the astronauts have landed on the moon.
Why are they being quarantined?
Well, this is a question that can be discussed, I guess, forever, but there is some concern that there are forms of life on the moon that perhaps could cause us problems if they're brought back here to Earth.
And an actual lunar landing crew will go into this facility and be brought inside in their sanitary container all the way back to a quarantine laboratory here at Houston. Now, what are you going to do on the carrier Guadalcanal in this test run of the mobile quarantine facility during Apollo 9?
Okay, the quarantine facility, the mobile quarantine facility, the systems have been built to house 6 people for 10 days. And on 9, we'll actually run through an exercise with people in the van, and they develop procedures and get a good checkout of the systems aboard the facility.
You mean some test subjects rather than astronauts will go inside the facility and be sealed up there for up to 10 days?
That's correct. Not really for 10 days, but we will put test subjects in a spacecraft in the water. This is a trainer spacecraft which we use here in Houston to develop procedures. We'll put 3 test subjects in a spacecraft and retrieve them, and they will enter the MQF along with a recovery engineer and a doctor for the trip back to Houston.
And they will be brought all the way back here to Houston inside that thing?
That's correct. They'll be offloaded from the carrier when we get into port, and then the facility will be transferred to a C-141 aircraft and will be flown back to Ellington, and from Ellington at Ellington they'll be loaded on a special transport vehicle and taken to the Lunar Receiving Lab.
Then how long will that end the exercise when they reach the Lunar Receiving Lab, or are they going to go on through the test in the receiving lab here, or the major quarantine facility?
Well, at the Lunar Receiving Lab, they are preparing some exercises to train their own people, but our subjects will enter the Lunar Receiving Lab, and how long they'll stay in the Lunar Receiving Lab hasn't been determined, but the scientific side of the Lunar Receiving Lab, they are planning to actually run all the tests and so forth on the lunar samples that we'll simulate bringing back, the biological samples, and some of the spacecraft data that we will be removing from the spacecraft.
Well, this sounds like a good time to get an actual exercise of this necessary facility during a flight when you have all the ships out there at sea.
Yes, this gives us a great opportunity. We'd planned to do this anyway, but we want to combine it with 9 because we have the ships for our use, and this way we get good use out of the ships during this mission.
But we want to emphasize the Apollo 9 crew is not going to go into this quarantine facility this time.
No, we intend to keep this exercise entirely separate from the Apollo 9 mission.
Thank you very much, John Stonecipher, Chief of the Recovery Systems Division, here in the Landing and Recovery Division of the Manned Spacecraft Center. Mr. Smiley, what has been done on this Apollo spacesuit to update it and to bring new technology to the fore to make it safer for astronaut Schweikart and others to perform out in the vacuum of space?
Well, I guess to answer that question, we'd have to go back into the history of the manned space flight effort, and in terms of what suits were supposed to do in each spacecraft program, to understand what we have done to the Apollo suit, because most of what we've done to the Apollo suit is in answer to the peculiar mission requirements that we must satisfy in the Apollo program. In the Mercury spacecraft, there was no requirement for any kind of extravehicular activity. There was essentially no requirement for any kind of specific ability to perform tasks with the suit in the pressurized condition. So the purpose of the suit was a backup to the pressure cabin, and as such, it functioned very well. We never had to use it because we never had a problem with the pressure cabin. But had we, the suit would have been automatically pressurized by the spacecraft environmental system, and the astronaut would have had that mobility that he needed in his hands and in his arms to be able to fly the spacecraft. In the Gemini program, as initially conceived, we again did not have a specific requirement for extravehicular activity, but very early in the program we determined that we should move in the direction of extravehicular activity and began to plan for it almost from the beginning. We put some effort into making the Gemini spacesuit more mobile in the pressurized condition. Since also that spacecraft had a little more room in it and the astronauts were engaged more in flying the spacecraft than they were in the Mercury system, we got as much mobility into the arms, hands, and the upper body as we were able to get. When we embarked on the extravehicular activity kind of development, we made as great a strides in that direction as we could. We still didn't do anything significant as far as walking is concerned, because any EVA in Gemini would not involve any extensive use of the legs. So the primary emphasis there was in the upper torso mobility improvements, and some of these were incorporated into the suit. In the Apollo program from the beginning, we had the requirement to be able to operate on the lunar surface, and as such we had a very real requirement to be able to walk, to be able to perform experiments, to pick things up, to take samples, and in general to do all those operations that were required for any kind of scientific exploration of the moon. So the suit that we developed for that was, prime objective was to incorporate the mobility into that system that would allow us to perform these functions. So we went to a different kind of a joint than we had used previously, which is a bellows at the elbows, at the knees, at the thighs, in order to be able to move more freely in the spacesuit. Other things that we did for operation on the lunar surface is to increase the amount of thermal insulation that we had in the suit. Still essentially the same kind of design that we had in the Gemini suits, but designed to handle the lunar surface environment. The other functions of the suit that we have to handle are mostly similar to the Gemini program, just tailored specifically for the lunar surface mission. We have the sun visor as we had in Gemini, but we have a more severe thermal environment, so it has to have improved performance characteristics. Another thing that we've done to the suit, different from the other programs, is to try to increase its resistance to flame, flammability improvements. The outer cover of the suit is now made of a glass fiber material called beta cloth. It's coated with Teflon to increase its durability. This material will not burn in the spacecraft atmosphere. I think that about sums up the peculiar things that we've done to the suit for the Apollo program.
Well, now, will other astronauts besides Schweikert be wearing the same type of suit from here on through the Apollo program?
Okay, essentially the suit that Schweikert is wearing is the same suit that will be used for lunar exploration. There might be some slight differences in patterning and things of that sort, but I think from a total standpoint, it's the same suit.
Well, thank you very much, Ed Smiley, for giving us not only the history, but the chronological development of the Apollo EVA spacesuit.
Thank you very much.
Ed Smiley, Chief of the Crew Systems Division at the Manned Spacecraft Center.